Well, thanks for your welcome, and good afternoon. And I'm happy to come over here. As I said, I joined NASA Ames in 1987, so I have memory of when Google had an SBIR contract, you know, single digits. But, and I live near Waymo, so I get to see the parade of vehicles passing by my front yard every evening around 10 o'clock, headed back into the mothership, I guess. So have watched with some interest, and am honored to have been asked to come out and talk a little bit about some of what I'm doing on the other side of Stevens Creek, along with my colleagues and peers over there. So the picture behind me, you could argue, relates to possibly, maybe not self-driving vehicles, but it is an autonomous rover, and in NASA's case, we tend to use those for moving our instruments and means of gathering samples and data to faraway places, going back to, in most recent Mars history, we've had Curiosity and the MER rovers back in the 2000s, and Pathfinder before that. And one of the follow-ons to Curiosity, or to the Mars Science Laboratory as it was then called, it was something called the Mars Astrobiology Field Laboratory, or AFL, having nothing to do with football leagues, but in about the 2007 or 2006 timeframe, there was going to be something based on the chassis and on the technology that currently went into what was then going to be the 2009 MSL mission, and with a 2-meter coring drill, a means to handle that material and get it up from underneath the surface, and then crush pieces of it, subsample, pick it apart. And why do we want to do this? Well, one of the things is that people are interested in looking for biomarkers, for signs of life. Could life have existed in places other than on Earth? The astrobiology question. You know, so this was a proposed mission to figure out, were there habitable zones, at least on Mars, and how those zones might have developed, and what does that tell us about Earth, as well as the evolution of Mars, and to look for any specific biomarkers or evidence if we found anything. There were concepts of this that went down to the point of specifying what it should include. It obviously had to have some means to get sample if you were going to look for, you know, organics or past cellular debris or anything else that might be stuck that might give you evidence of it that was once habitable. There needs to be some means to get the sample in the first place. So it had, I guess, as I said, a 2-meter drill, sample transfer, could subsample cores, could deliver these things to instruments. So self-driving and self-handling and self-drilling. However, if you're looking for life, this complicates things. The current Curiosity rover is not sterilized to the levels that would be necessary to send it into what we call a COSPAR special region. A special region is a place where maybe, just maybe, life could exist under some conditions if you happen to introduce the right microbe and you happen to worm it up and put it in the right, you know, basically places where you could maybe terraform by accident if you weren't careful. So we don't want to do that, especially not unintentionally. You know, you can talk to your favorite science fiction author otherwise about the advisability of this, but you know, we have agreements that we are going to try to protect other planetary environments, not just despoil them, as it were. Also, if you're looking for signs of life, you have to make sure you're not just you know, looking at your own foot, so to speak, that you're not simply discovering the microbes that or the biomarkers you brought with you. So contamination avoidance, you have to be very, 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 very clean, both to protect where you're going and to make sure that your results have some validity. And then how would you know if if there was life there if you saw it? Now you might find weird life, silicon-based, or something we haven't even imagined yet. So it's, you know, it becomes, how do you detect something you don't know about? But you can at least come up with instruments to detect Earth-based life. So all these were concepts of this astrobiology field laboratory mission that was supposed to follow and eventually became the 2020 rover, which is not an astrobiology field mission. And maybe in the 2020s we will get an AFL mission, and that leads us into ARADS in some sense. Because after the AFL idea was shelved, there's the desire to figure out how would you look for signs of life? How would you take a mobile platform? How would you subsample? How would you drill? Those issues didn't go away. So it was sort of inspired by the astrobiology field lab rover concepts. Starting about 2010, after AFL was canceled, we started putting together proposals and working and tinkering with them. And in 2014, we put together the proposal shown here with a rover, a 2-meter automated drill from Honeybee, a sample transfer arm with a scoop on the end of it that could either scoop material like the Phoenix mission or could take powdered cuttings or material from the drill and carry it over to instrument. It could do double duty in a sense. As well as instruments, if you think back to those AFL calls for looking at habitability and as well as for signs of life, well, we had a refly of the Phoenix's wet chemistry laboratory, discovered perchlorates on Mars, and half of the ExoMars planned MoMA instrument, basically a laser desorption mass spec. That way we don't have to incinerate our sample, so using the laser to ping it, in effect, we can hopefully catch the right ions and we will detect things that we otherwise would just incinerate if we have to do pyrolysis and heat it up. The Spanish solid instrument, signs of life detector, is an immunoassay. I sometimes joke to folks, it's like sort of like a 512 home pregnancy test printed on a chip. That's gross oversimplification, of course, but it is an immunoassay. You're looking for specific molecules or specific compounds, specific to organisms or specific, you can pick your favorite amino acid. You only get a grid of them, so if you don't pick the right 256 or the right 512 and you get something else instead, you don't see it. So that's the drawback. On the other hand, you can look for a lot of different things and it will fluoresce and it will tell you if you've got a positive hit, just like with many medical tests now. And finally, there has been an instrument called the chemical laptop, a electrophoresis-based microfluidic instrument developed at Berkeley about, at this point, 12, 14 years ago. And the descendants of the chemical laptop in various places are being developed into instruments, both at JPL and at NASA Ames, actually, as we speak, and put into various mission proposals. The microfluidic life analyzer is one of these. It's coming from JPL in this case. And it would be able to give us amino acids and their chirality, and we could have some idea of what we are looking at and if this is from a biogenic origin or not, based on what we could get from that. So we put this together as a package, proposed 4 increasing capabilities, starting from basically just taking the pieces out to the Atacama, to putting things on the rover with the drill and the arm, to then integrating the instruments, and then finally operating the whole thing remotely from the US in sort of a mission-style operation. So got picked in early 2015, and with our partners at Honeybee and in Spain and JPL and Goddard and so forth. So off we went. The basic concept is we will go to a Earth analog site, something that has some aspects or some attributes that are similar, if we feel is similar in some respects, to another planet. In this case, we were looking for some place with a very low bioburden. It's very dry, very desiccated. It's not as dry, desiccated as Mars, but it's the driest place on Earth. So we can get some of the same effects. And if we are looking for life in desiccated, dry places, well, this is a good place to test the same techniques, at least at a first cut. We would make field use of astrobiology sort of prototypes of flight instruments, and at the same time grab samples that we can take back to our lab so we can compare the performance of the flight instrument versus the tabletop, expensive, well-calibrated, well-tuned instrument that can get 2 orders of magnitude more precision, probably, than what we can put onto a rover. we would have, since light speed means that on Mars, that plus the Deep Space Network only gives you 2 windows a day to talk to your missions. That plus the 10 minutes in each direction means that whatever you send out there has to be autonomous. It not only has to be self-driving, it has to be self-drilling, it has to be self-transporting in terms of samples, and the instruments all have to be able to not burn themselves up. And so the autonomy and the software implications of this are significant. I mean, just the drilling alone is something that on Earth still is pretty much a human-dominated activity. Even deep sea drilling with the oil and gas industry that's done remotely is done joysticked with people in Houston or similar places doing VR work, but you have human operators just as if they were flying drones. They're essentially flying the drill while on the bottom of the seafloor. It's still a human-governed, that kind of reaction time. And finally, we have to know if anything we're discovering is valid, so we have to have a control. So the best field science, and also to study the desert and the Atacama as a Mars analog in and of itself. And I'll skim through some of this, I guess, but this is just to put it into context. How we were addressing science was in terms of figuring out what are the limits of life in an extreme environment, and do we find biomarkers there on the surface? More about that later. And is this a good Martian low to mid-latitude model? In the technology sense, there's the software automation and autonomy, surface mobility, and drilling, integrating those together. Yes, Curiosity has a drill, but it has a 5-centimeter drill about the size of my thumb, designed for sampling outcrops. And it doesn't get used that often. It's quite an engineering challenge as it is. And then science operations, how do we do remote surface operations that involve this much complexity, transfer, and analysis, given the light speed and the bandwidth limitations that we only get to talk to the vehicle twice a day? So we went out saying, well, we address all of these things. We have a nice AFL-looking proposal, and the folks within NASA headquarters who look at these things said, yea, verily, go forth. Because they're operating off of Astrobiology roadmap, which has been revised, I guess, 2 or 3 years before that. And just not to belabor, since most of you are probably familiar with the main, where do we come from? Are we alone? Although that's as much of a SETI question, but how can we detect whether that's microbial or complex? And then what does that tell us about our own future? We strive to investigate a bunch of different science goals, but the ones that are most relevant here are how would early life interact and evolve with a changing environment? Because the environment in the Atacama in Chile changed dramatically over the past few million years, and when it's been gone to a very dry, desiccated, in some respects it may be a good model for what could have happened billions of years ago on Mars if we look at early Mars versus going up to the present. It also gives us an idea of how to look for habitable environments and how to recognize signatures of life by looking at, do we find signatures of life in this very barren, hostile environment? So astrobiology is a motivation, but at the same time we have to find a place. There are no perfect Earth analogs. Everything is a partial, because we're not on Mars, we're not on Europa, we're not really, everything is, we may be very dry and desiccated in Chile, but we're hot, we're not cold, and the ambient pressure is way too high. I can go to the dry valleys in Antarctica, we've tested there with past drills and instruments, and it's pretty dry, although not as dry as the Atacama, and it's cold, but again, the ambient temperature and pressure, and it's a little bit wetter. I can likewise go to the Arctic, to a big impact crater, and the soil has been broken up. You have something very akin to regolith from the meteor impact, but it's a bit wetter and it's not as dry. So you take your pick. You can sort of have some Venn diagram of possible characteristics that look like Mars or other places, but you can't have all of it. So we decided to take this to Chile. We looked at 3 sites, one near Ipicaca, one at Maria Elena South, which is listed as number 3 there on that chart, and one at the Yungay Station, ghost town, about 90 kilometers east-southeast of Antofagasta. And pictures of these, there are gypsum polygons, there are eroded formations, there are salars with halite deposits and salt crystals that actually hook up as though they were arms coming out zombie-like out of the ground. We ended up sticking with number 2 at Antofagasta, both because it has a variety of things. It's drier than anywhere except for maybe number 3 at Maria Elena South. And it has a derelict sort of ghost town, abandoned agricultural station, which we can outfit to support us as far as the logistics go. But this is a very barren place. One of my cohort, one of the folks working on this on the field science side, Mary Beth Wilhelm, is about to publish a paper talking about a transect going from further south to the north, from warmer and from cooler and wetter to hotter and drier. And this is what she's finding. These are actually early results from this past field season. A little map at the bottom tells you roughly the geographical, although that's, again, read instead of left to right, that's really kind of south to north. But it shows that as you go from merely extremely arid to hyper-arid, the markers like cyclopropane, the second chart down, go to 0. The LD chip total fluorescence, that's solid. That is, again, from this year's testing, we saw that samples fed to solid. By the time we get to Yungay, we have something like 8 out of 256 that we are still seeing any positive hits on. Same thing, fatty acids fall down. Basically, they're the signs of life or activity diminish to almost nothing by the time we reach Yungay or Maria Elena South, which is even further over here. So in that sense, it's probably a really good analog site. And again, it's a good simulant for what we might find at Mars. Again, the pressure's too hot and it's too warm, but it's very dry, very desiccated, and we're not seeing signs of ongoing activity. And again, from Mary Beth's work, this is in press currently, we see changes as you go from the south to the north. And this is looking at this transition zone from biologically active, where we see at least a few occasional endoliths, things growing in rocks, or a few plants or lichens, a little bit of biomass, to places like Yungay or Maria Elena, where there's no visible activity, low biomass, and when we say significant racemization of amino acids, what that indicates is they're decaying. Typically, they have been irradiated and they're breaking down. It's dead stuff, Jim, basically. It's very dead stuff. Most of what we were finding was on the order of 10 to 40,000 years dead stuff, just in the surface soil. So there's not much activity, and most of what you find are microbial skeletons that may have even blown in some distances from other places. So that was sort of framing why we went to this particular barren place and what collection of stuff we wanted to take with us and why. So a little bit about, well, what did we actually go out and do, or what are we in the middle of doing? The first year we went out, did some of these studies that you just saw displayed here, and sampled at Yungay as well as some of the other sites, Maria Elena and the Ipicaca site. We took 2 instruments, the wet chemistry lab and solid. You saw some solid results on that previous chart. Wet chemistry lab brass board, even though it flew on Phoenix, what we have is had been in storage for about 6 or 7 years and was a brass board, not a full flight unit, so we had to renovate that. We started work on the 2 instruments we didn't have in hand, and we got a new drill and a new robot arm, since the ones that we had originally proposed broke. And that's part of the downside of taking things out and trying to break them, is sometimes you succeed. And it's not necessarily a bad thing, but you want to break things, because if you don't break things, you're not learning and you're not able to improve and go and come up with things that won't break later. But still, you have to keep putting things together then. And I keep having to justify the budgets. So this year, in February 2017, our objective was to take the KREX-2 rover, which is a vehicle from, Terry Fong is here in the audience. It is his group that has developed this as one of their stable of rovers over the years. So in collaboration with that, we have a honeybee and NASA drill that you see up to the upper right, kind of sticking up, kind of a gold spindle with a long shaft protruding, and MDA Aerospace, sort of a Canadian contribution, I suppose, although it's a U.S. subsidiary, arm with a scoop on the end of it. And they did the Phoenix and Insight arms and helped JPL with the Curiosity arm, so they have a long track record. Honeybee did the rock abrasion tool for grinding things away from the MER rovers and the dust removal tool on Curiosity. So these are all entities with some direct experience in flight hardware. So this is it, sitting in the Atacama as it was after nightmares of getting it through Chilean customs. Included in this rover, we have 3 different robotic subsystems. There's the KREX-2 rover and its own autonomous navigation. You see it there, even though maybe the perspective isn't as good, but the tracks left by the rover as it trundled up a hill, that's about a 15-20 degree angle, although again, since you're looking uphill, it's not quite as obvious. But the rover is going and finding its own way around the boulders and obstacles in its path. We have the arm that, again, from MDA Aerospace, something we're not usually always scratching our head when we look at it, but and then we have the latest generation of Honeybee Robotics rotary percussive, lightweight, 15 kilo, 2 meter class drills. Usually the deal there is that Honeybee designs the mechanics and we usually write their software over at NASA Ames. So we do the drill control, they do the drill mechanisms. Usually we don't fight each other too much. The rover itself will carry 4 instruments, maybe a 5th, maybe 3. We will see this. We'll develop. The arm will deploy sample to individual instruments, one after another after another. We're just taking a scoop and basically dumping dirt in 3 different physical locations. And it can autonomously navigate. And possibly even we'll be able to identify, if we get a little bit of supplemental support, good locations to drill on its own. That would be a coup if we can get that in a couple of years. Rover navigation. This is just showing one of the Atacama from this past season. I believe it might have been the same run you saw it trundling uphill. Just the rover both does image processing for navigation. It has a LiDAR mounted on it as well. We have to be careful with the LiDAR. We take it to other countries because it's export controlled. But nonetheless, it can autonomously find obstacles, navigate, identify, and do a limited amount of contextual analysis that we might be able to leverage in future years. The robot arm replaced our old robot arm, which eventually we killed. Again, this is sort of a track family history from the Insight and Phoenix arms. We just got this. We have been tuning it ever since. And the software for controlling it, of course, is the biggest problem because we didn't want the flight code because we want to operate it on a laptop or on an embedded thing off the rover. So they had to write something new for us specifically, and we're still working with that. But it is not killed anyone yet. There was once upon a time an apocryphal story of somebody violating buddy principle rules around a robot arm in a lab late at night on a Friday, who then had forgotten to set the safety perimeter up. The system got activated, came around and scratched them, at which point they ran down the hallway shouting, "I need medical help, I've been attacked by a robot." That's only somewhat anecdotal, but I'll leave it at that. The new drill, which is the 5th generation of lightweight planetary prototype drills that we have broken in succession, was funded by a combination of projects. 2 of them are ones I'm working on, ARADS, and another one that will be going to Spain in 2 months, and the Resource Prospector project, which is currently in sort of a pre-phase A state at NASA Ames and elsewhere. It's a joint 15 kilo 2-meter capable, although most of the time we only operate it with a single drill string, so that's about a little over 1 meter. And it is able to operate into about plus 70 C down to lunar equivalent minus 230 C temperatures. So it's ruggedized and designed to be able to be cold world or sort of Europa compatible in that sense, or lunar compatible for resource prospector. So we took this out, we bundled this together, we integrated, we drove it, we braved the dust devils and customs and shipping and all the other constraints that sometimes get in the way of doing some sort of a technical test out in the middle of nowhere. And we're successful in getting not quite 14 meters, but that was doing actually darn good considering. The deepest was full stroke, 2 meters. And we saw 3 of the 5 major fault modes simply occur in the course of Mother Nature, binding or over torque. Basically, if we have something that we are going into and it grabs the side of the auger, in this case, corkscrewing, which typically comes when you try to retract. If it catches on an edge, suddenly you're in tension. It's like you're trying to pull a cork out of the bottle, or you're trying to unscrew it, and it's not unscrewing the way you would like it. Or hard material, which can also be a worn-out drill bit or something else that is causing your rate of penetration to go to 0. So we found some nice ways in which we can fault or break the drill while it's on the rover, so we can then look at how does being on a suspension or minute movements in the rover platform affect compared to a lander platform or something that's more stable. So those were all very useful for us. We also managed to demonstrate that we could take the dirt, the sample that was coming up out of the ground, and transfer it. Since we don't have the instruments on it this past year, we could still send it to a catchment bucket or a sample jar on the back. In one case, we did put an instrument back there just so we could say we'd done it, but that wasn't really an integration. But still, successful. We should also, as you see here, and on the opening chart, when we were testing, we have to clean very thoroughly with about 4 successive levels of solvent between between sampling. So, and we don't want to breathe on it or bring our own microbes, so we have to wear bunny suits, masks, hairnets, booties, which when it's already 100 degrees and you're in the sun and you're in a bunny suit, sweating, bending over and trying to swab small amounts of either alcohol or something stronger solvent-wise, that's tough work. But it was necessary every single 10-centimeter sample. So when we did clean samples, it was time-consuming, and you see them in the middle here of the cleaning cycle, and someone back off about 20 or 30 meters who's recording the data from the previous sample set. For anyone who is into penetration rates and the hardware involved for the drill, this is a comparison of the new drill versus the old drill. The biggest thing here is really the stroke length is improved and the mass is a little bit higher from 13 to 15 kilos, but we have a lot more torque that we can play with, which keeps us from getting stuck. The old Lita drill would notoriously wimpy in some materials if you went into basalt or if you went into solid ice. I once had to dig one out in the Arctic with the Lita drill, and ARADS should not have this issue. Good thing if we're looking for ice deposits for the resource prospector folks. We don't want this getting stuck in ice. And again, Honeybee does the hardware. NASA Ames typically does the software. We leverage our M-Slice sequencer and take some diagnostic modules that we reason about. We have some ordinary limit checky, expert system-y stuff. We look at vibrations and do some genetic algorithms to basically do the frequency shifts and process the frequency shifts in real time. And then we do a little bit of model comparison to see if it's behaving the way we think it should be behaving. We have to arbitrate all of these down at the bottom where it says diagnostics, and then decide with exec that we are, what recovery action, if anything, or what parameters to shift in real time. And we have to handshake, We keep flipping back and forth. We were originally going to use 0MQ. I think we are just back to DDS now in terms of how we handshake and what we do with honeybee. One other aspect of handing material, assuming we are successful in our automated drilling and the rover has positioned us and we have something in a scoop, well, we have dirt, okay? We have pulverized rock, well, so what? But instruments have to be automated too. If I have an instrument that's designed to only operate on finely milled, floury particles, and they're going to extract, and I dump a bunch of gravel in it, then I've just killed my instrument. Mission over, or at least that instrument's over. So this led to lots of gnashing of teeth and a discovery proposal I was working on in the 2013 to 2015 timeframe called Icebreaker, where we had huge fights among the team working on the proposal, back and forth, across institutions, screaming and yelling, and project managers being replaced all over this one issue of, can we take the risk of screening or not screening sample particles being fed to it from a drill like this? And because we had an instrument that couldn't handle anything bigger than about 2 millimeters diameter, or it could handle maybe 1 or 2 2-millimeter or bigger particles, but nothing bigger than that. And so did we need to build a SASPA, like on MSL, a complex filter screening, 12 motors, lots of degrees of freedom, or could we just have a simple screen or not screen anything and just say, well, we might get a bigger rock, but we probably will happen so infrequently we're not going to worry about it? I was in the latter camp. Other people were in the former camp. Since they're not here to defend themselves, I won't revisit that argument, only to say this shows this is an important thing that, well, the next time we propose this in a year or two will undoubtedly be used as ammunition by both sides. So if you look at this, you can see that the distribution is mostly in the 0.5 millimeter, 1/4 millimeter, in the 500 or 250 micrometer range, if you look at the proportions of the bulk here. And if you go all the way out to the 2000, which would be 2 millimeters, it's a little tiny bit, 3%, 1%, 4%. And the 60, 120, and greater 130, those are depths brought up from as far as drilling goes on average. So the stuff that we would really kill about, the stuff that might cause hiccups, are the 4 millimeter sized particles. And one of those we have none, and the others we have just a tiny amount, 1% of the sample. So if we're only doing 10 samples, let's say, on a given mission with a given instrument, 1% might show up with a rock. Okay, so maybe in 1 or 2 of those 10 we might get a rock. We could probably keep operating with that. So this is a useful result when we're making those sort of risk assessments, or will we jam up our internals of our instruments? If you think back to the description of the Astrobiology field laboratory, one of the things it was concerned about was contamination. Not just how do you sterilize it, how do you make it very clean when you bring it, and that's sort of comparable to the people you saw in the bunny suits, making it clean in that sense, but also how do you know you're not just observing the life you brought with you? Suppose you were contaminating your own mechanism for detecting life. So we have needed to study this and get some sort of a handle on it. So we have done some tracer studies. This shows one from this past February, where we essentially took hydrogen bromide spray and laid it across the area we were going to drill into, then drilled through with a cleaned, sterilized drill after we had backed away from it, and see what concentration of the bromine shows up in the samples coming down from the surface. Okay, then the one in the center, we actually sprayed the tracer on the drill bit itself in a different hole before it went down below the surface. So one of the things this tells you, we also tried to control for how often is there percussion, the little hammer signs, or do we see any moisture in the hole, the little droplets. As you might expect, if you're just drilling one hole, as you drill, a pile of cuttings builds up. Those of you who've used a hand tool, if you do home improvement or something else, you drill into something, a little pile comes up the auger and deposits itself near the borehole at the surface. And once you've drilled enough and enough stuff has come up, some of that material starts falling back down in the hole again as you shake it or bump it around. So here you see that as you went deeper, you started seeing more and more of the tracer. And you might say, well, that's counterintuitive. The tracer was on the surface. Why are you're going deeper and further away. Why are you seeing more in the samples you're bringing up? Well, the answer is that you weren't seeing material you had brought with you were seeing circulation. You were bringing up particles, dumping them on the surface as you drilled deeper, which then fell down again, back down in the hole, and sometimes made a couple of cycles of this, and each time they would carry more tracer back down the hole. So something at the surface in proximity could actually be more of a problem to some extent. Now, I suppose if you went really, really deep, if this is a 100-meter drill, I imagine this would taper off at some point as far as the effects go. But down to a meter, this is what we saw. When you sprayed it on the drill bit, that's more or less straight across. You might have seen a little bit of tapering off just as you were finally wearing. Of course, the levels are higher than just what was coming down from the surface. And then finally, when you would drill a little, bring it back up, drill a little bit more, bring it back up, you were sort of both exciting the material on the surface and exposing the bit to it as you went in and out of it. So it was a bit higher than the first case, but not as high as the second case. And again, there may have been some attenuation going on. As you bring it up and out, you knock the pile back, so less of it was falling down after a while. So again, cross-contamination, we don't want to introduce our own microbes into our instruments, so we have to get an idea of how do we drill cleanly, and is this going to be a problem with our own contamination? And it looks like it is. A little bit about our instruments, and I'll wrap this up with the wet chemistry lab, 10 kilos, flew on Phoenix. We've taken it out there already. It detected perchlorate on Mars in 2007, so it can give us the habitability and the background of what we're looking for. The signs of life detector, I talked a little bit about this. It's an immunoassay. It can look for a grid of potential molecules or markers of past life, and can operate in the presence of perchlorate. It doesn't heat anything up, and it's an antibody match. And some examples, so if you notice as you go down, you may see antibodies matching differently. This is from some 2016 data from Pit 2, near where you saw the picture of the rover before. Notice you got way more signatures when you got to 80 centimeters depth in this case. Big signature there, and then suddenly you go 10, 20 centimeters back to almost background levels again. And at 130, there's hardly anything. You also, if you notice at the surface, in that particular pit, or in that particular hole, there was hardly anything. The desiccated upper surface, and much of what you're seeing at 80 or 100 at a meter down may be a couple of million years old fossilized material. From this year's data, you could see that after those 256 or 51 potential hits, you only saw about 8 proteins as far as the solid, or in this case, LD chip, if you take it out of the solid case and you're doing it in the lab. And here's a comparison of Youngay's results with those of some of the other sites. This is also from Mary Beth's paper. The Mila microfluidic life analyzer, you can see a picture of the chemical laptop in the upper left corner. It does an excellent job of amino acid analysis, potentially, at least for a portable unit. It looks a little bit like, in practice, like a Mr. Coffee sitting on top of a laptop. So that's an inglorious way to refer to it, I suppose. But we did have it up and running in the field, as we see here. There's the extractor. It's not, well, that's really not a Mr. Coffee. It does have a funnel on the top, but that's way more, no coffee grains in that at all. But then you see the chemical laptop in the back. So the two were operated separately and off to the side with samples that we basically just carried it from the rover over to the field to give to the Mila folks, and they did their analysis. Next year, we will have the laser desorption mass spec. Again, it's half of the ExoMars MoMA instrument. Of course, as ExoMars has continued to slide, when we proposed this in 2014, it was going to be a 2016 flight. So we were going to have this already tested, already flown instrument that we were simply going to leverage. Now it's slipped to 2020 and may go to 2022, who knows? This means, though, that they are, we're now still working with the engineering unit, and as they look at their own design and redesign cycle, so they have a harder time getting hardware ready for us. So their schedule has slipped. They didn't make it in time for the February field test. They also have to operate in a vacuum chamber. So we have to create a Mars atmosphere inside a cylinder that we are pumping down, trundling along on the back of the rover in the Atacama. So in some sense, we have a sort of Mars-like environment here, and we're recreating the atmospheric constituents for this instrument as we go along. Something we had never really anticipated, but we've been playing around with, the MinION nanopore sequencing, which you can get for about $1,000 from a company in England, Oxford Research, I think. And there's a picture of one held next to a halite nodule over in one of the salars. You can see it's the closest thing so far to a tricorder in the sense of being able to identify and sequence something and identify organisms and do synthesis. What microbes are here? And here is one that we weren't expecting to see, Selenobacter. You see the little thin blue wedge at the Yungay Salar in 2016. But it's comparable to the PCR and centrifuge traditional DNA sequencing approaches, but you can do it in your hand from a laptop as long as you can keep it cold. And some more MinION analysis and data from this past year showing both the archaea, bacteria, if we're looking for extremophiles, even viruses, and then the halite-liking versus non-halite-liking splits in archaea and bacteria respectively. We've also taken our field science samples and done offline analysis, both to study Yungay and study the region better, and to also provide a control for what we're doing with the instruments. And one of the things that Jocelyn DiRuggiero, one of the team members from Johns Hopkins, found is that she had taken samples in the area in 2013. In 2015, there was a rainfall event, very, very rare there, and she noticed a significant shift in the populations. Bacteria were much more diverse compared to the archaea, the extremophiles, and they were out-competing the salt-in strategist, as it were. And cyanobacteria, which you hardly ever see in that area, were suddenly popped up to noticeable numbers. So this was an interesting sort of shift in terms of climate change effects, even in the Atacama, in these halite populations of microbes, just as a side effect of doing this for the sake of the project otherwise. And this compares traditional methods to the results with the MinION, so fairly comparable, and we'll probably go forward with that. So things to wrap up that we are currently doing: we finished our field deployment. We had our initial MELA test. We have the laser desorption mass spec going to a vacuum chamber in June. In the autumn, we will be taking these instruments and instrument mock-ups and putting them on Terry's rover there, along with the drill and the arm, and seeing if they will all fit. And if we drive them around and bang them around and get them all dusty, will they still work or will they fry themselves? We'd rather find out if they fry themselves here in Mountain View rather than taking them to the Atacama. And we'll continue to do sample analysis and do our vibration, thermal, and power environments characterization. So that'll take us to maybe next February or March to year 3. So the multiple steps, we have done 2 of them. The first 2, 2018, we'll put the instruments on the rover. That will be locally controlled, except the LDMS will probably be operated on the side still, given they're lagging now. And then leading to 2019, early 2019, we will operate this as a mission sim to at least some level, sending it commands remotely from NASA Ames or other places. And that concludes what I had prepared for y'all. We got about 10 minutes, I guess, for questions if anybody's interested. Thanks.
What's at the bottom of the hole on the slide?
What's at the bottom of the hole? This is a 2.5 meter deep pit that has been documented in the literature. Actually, has been in multiple papers. It is over about 10 kilometers west of the Yungay station, sort of the ghost town area, but is one of the primary research areas and where the samples that are labeled as yunge come from the vicinity of this. Because we actually, without using a drill or other means, this was dug out with people in bunny suits with pickaxes. So if you can imagine being carefully bundled up to avoid contaminating what's down at 2 meters down, because if you've got tiny traces of organic material and biomarkers, you don't want to spit on it or sweat on it. So you have to be bundled up, and you're in 100-degree heat, and you're digging something, and you're below the level of this. So you can imagine how much of a adventure that has been by 5 or 10 years worth of successive graduate students doing their Ph.D. dissertations coming to this location, among others. Also, it makes a nice looking up at the field science crew photo, which is, I always thought they looked inquisitive, so I like to use it. So, in the back.
My question is about the rover. Is that the final look and feel of the rover that's going to Mars? Because I noticed some difference, like this is 4-wheel versus like usually they're 6-wheel. And is there anything you guys learned from the current issues with the wheels, like damaged wheels and aluminum wheels?
Well, there are mobility architecture issues. And of course, the irony, of course, is you're sitting next to the rover guy, as it were, in the audience. So this is really his rover, but not everyone is wedded to the rocker bogie architecture that you see on the Mir rovers or Curiosity. It's one among several. There are advantages in terms of maneuverability and getting yourself in and out of things between just a rocker architecture independently like you see here. We did have to, though, look at, if you notice, we had rubber tires, and while that probably wouldn't go to planetary surface, because rubber is organic. Anyone who walks along a highway, you see bits of rubber that are shed by tires, so you're thinking, well, aren't you going to contaminate your samples with bits of rubber? So we actually needed to drive the rover over ground before we drilled it, and then take the drilled samples and surface samples and send them off for analysis to see if we were getting appreciable contamination, not from bromine, but from tire rubber. And we've had to look at that and things like outgassing of solvents and things well. So in terms of the long-term rover, it probably really is a function as much of the intended surface roughness and sort of the masses, the sandy versus firm, obstacle size, the dimensions of the obstacle. There are architectures where you might be better off with treads, depending, although treads are pretty heavy. So I would not say that the dual rocker architecture is inherently superior for Mars or Europa. It's really a trade-off or a trade study according to your intended environment. Over on the side, blue shirt.
You mentioned earlier on that one goal is to have the rover be able to determine what is a good place to drill. So my question is, what constitutes a good place to drill, and how would the rover go about determining that?
What is a good place to drill? The way a geologist or an investigator in the field would choose this, if I were working for an exploration company, I would want to do seismic or other geophysical surveys and have some idea of the strata and what lies underneath my feet or underneath my wheels, figuratively speaking. Problem is, on most planetary surfaces, we're not going to have that. We might have something at tens of meters scale that we've gotten from ground penetrating radar or from some sort of remote sensing. But we're not going to know down to the meter scale probably of what's down there. So how do we know that there's this interesting feature 2 meters down here, but it's not over there? So we can only go by visuals and surface. And we can look for patterns, things that look like outflows, things that look like fractal structures in the soil or on rock surfaces. We can also do the logistical or practical side of obstacle avoidance. Let's not drill or position ourselves over a boulder or over something with a sharply canted surface that is going to deflect our drill and make it just operationally difficult to go through. So if we can handle let's at least find a nice flat space to drill as opposed to the top of a boulder, that's at least doing sort of our bottom levels, Maslow's hierarchy will at least not do any harm. And then if we can work it up and start picking things that are visually more interesting, we can start weeding out all the bulk of the things that are less interesting. And even if I can throw away 85% of the potential drill sites, including the tops of boulders, that means I've just narrowed it down to 10 or 15% of interesting spaces. And while those still may be boring in the end, I'm still a lot better off if I can do that, especially if I have to let the rover make that decision because of the communications lag and the bandwidth issues. And we are talking about, how would you incorporate remote sensing data? There are folks colleagues who are working on that now. How do you incorporate visual images from a rover or from something and whatever remote sensing you've got to try to figure out where to prospect or where to drill? Where does X marks the proverbial spot? Any other questions? Well, in that case, thank you very much for your attention and for inviting me over. And if anyone is interested, I have a few of our most recent mission deployment patches here for your taking as you like to go along. And feel free to grab one. Thanks again.